So we're going to get started now. So I'm Eliot Quataert from UC Berkeley. I'm going to give 2 lectures on what was originally called, I think, just plasma astrophysics. And then it became an introduction to plasma astrophysics, and then it became selected topics in plasma astrophysics. As I think all of the speakers have emphasized, these are very large subjects that we're trying to cover. And so there's necessarily a set of choices that we have to make. And so really what I've ended up doing is I'm going to focus today's lecture actually on talking about winds from stars and using the physics of stellar outflows to introduce a number of key ideas that show up in many other areas of astrophysics. So these are winds driven by different physical processes, gas pressure, radiation, and then magnetic/rotational effects. These ideas come up in our understanding of outflows from galaxies, outflows from accretion disks, angular momentum transport in accretion disks. Many of the kind of key ideas in those fields actually originate in our understanding of outflows from stars, and so that's a nice way to introduce you to some of the topics. And then the next lecture, which will be on Thursday, will actually be on a very different topic, which is on understanding some of the properties of linear instabilities in fluids and in dilute plasmas, what the connection is between those, why we care about linear theory when we can just simulate everything, things like that. I also want to encourage you that if you have questions, to feel free to interrupt me as I go rather than wait till the end. So I did want to start just by giving you a bit of an overview of the range of astrophysical systems and techniques that you'll be hearing about kind of in the remainder of the next few weeks. So we're interested in our studies of plasma astrophysics in both systems that are primarily relativistic, either involving bulk motions that are relativistic or relativistically hot plasmas. And there's actually a range of different techniques that can be used to describe relativistic plasmas. So when the energy in the plasma greatly exceeds the energy, when the energy in the electromagnetic fields greatly exceeds the energy in the plasma, you can use something called force-free electrodynamics, where you kind of neglect the energy in the plasma to describe the dynamics of the system. And this is used for instance, in studying the properties of the magnetospheres of pulsars and understanding emission from pulsars. Then there's the general relativistic extension of magnetohydrodynamics, which you'll hear more about from Sasha Tchaikovsky. There are particle and cell methods for describing individual particle motions and the actual intrinsic kinetic theory of the relativistic plasma that Anatoly Spitkovsky will talk about. And then in some ways, the most relativistic systems of all are systems where you have to evolve the space-time as well. So collisions between neutron stars, collisions between black holes, and Luis Lenner will talk about that. The other regime where there's actually a very similar set of techniques is where we are not worried about relativistic motion, so the non-relativistic limit. And again, really the same 3 sets of techniques apply there, with the exception, of course, of dynamical spacetimes. So there's force-free models where you neglect the pressure or the forces due to the gas. This is very useful, for instance, in understanding some properties of the solar corona. Then there's kind of the bread and butter theories of MHD and kinetic theory that we've already started to hear about from Matt and Jim. And within these fluid theories, there's actually a huge range of different models that describe different plasma conditions and that apply to different astrophysical systems. So for instance, if you're interested in relatively dense systems where collisions are common, the mean free path is short, then ideal MHD might be a reasonable first approximation for the dynamics of the system. But even in this regime, if, for instance, the energy in the radiation is dynamically important, as it is in massive star formation or in luminous quasars, accretion disks around black holes, then you really have to consider a 2-fluid system where you have the radiation and the gas together. So that's an extension of kind of the fluid theory to include radiation dynamically self-consistently. And this is something that I'll touch on and that Jim will talk more about next week. And then there are regimes of dense plasmas where the ionization fraction is low, so there's a lot of neutrals around, the temperature is low, hundreds of Kelvin in the interstellar medium, and where you can't assume then that everything is well coupled to the magnetic field because there's lots of neutral particles around. And there's different ways of handling that fluid limit. There's the non-ideal effects that Matt talked about, resistivity, the Hall effect, and bipolar diffusion, very important in star formation and planet formation. And then in addition, there's the complication that there's actually large molecules slash particles that we generically call dust grains that are dynamically quite important because they absorb a lot of the charge in the system. And so another multi-fluid plasma is where you consider the gas and the dust self-consistently together. So this is all kind of within the rubric of MHD. These are the different microphysics that you have to worry about in different astrophysical systems. The other limit where we worry about deviations from ideal MHD is the one that Matt touched on today, which is the low collisionality limit, where we worry about things like anisotropic conduction and viscosity. More generally, we worry about the pressure being a tensor, not a scalar, and things like that. And so I'll touch on this a little bit as well in the lecture next week. So this just gives you a sense, really, of the large diversity of astrophysical plasma physics. Depending on the systems you're interested in studying, these different techniques will need to be brought to bear. What I'm going to focus on today largely is fluid models, including a little bit of effects of kinetic theory, and next time in my lecture on Thursday, I'll touch on even more some aspects of kinetic theory. Okay, so that's kind of some broader context. What I want to focus on, as I mentioned, is understanding outflows from stars, really as a great astrophysical example of introducing you to a range of physical processes and a range of techniques that show up in many different areas of plasma astrophysics. And I'm going to organize this by studying basically different ways that outflows from stars are launched. One is by thermal pressure, which is kind of the underlying mechanism launching the outflow of the sun. Then there's stars that are more rapidly rotating. The dominant kind of source of energy for the outflow is actually the rotation of the star tapped by the magnetic field. This is generically known as magnetically driven outflows or magnetocentrifugally driven outflows to highlight the combination of rotation, magneto, and centrifugal forces, rotation. And this model of outflows driven by the combination of rotation and magnetic fields is particularly important in the theory of accretion disks, and this is something you'll hear a lot more about. But the simplest context in which to understand this theory is actually just magnetized rotating stars, and so we'll talk some about that. And then the last example of outflows from stars is outflows driven by radiation pressure, where it's really the momentum of the photons being transferred to the gas which drives the outflow. So you have enough momentum deposited in the gas to overcome the force of gravity, and that's what actually drives the outflow. And this is generically described by the luminosity exceeding the Eddington luminosity. The Eddington luminosity being the luminosity where radiation pressure and gravity balance. So if the luminosity is larger than that, you can drive an outflow. And there's different ways of doing that. There's different ways that the photons can couple to the gas efficiently to drive an outflow. And in particular, I'll mention two different mechanisms which are relevant in different types of stars. And then at the end, what I'd really like to stress is that all of this physics described in the context of stars actually applies to a wide range of other systems. Galactic winds, in particular, a lot of this theory is relevant to the theory of accretion disks that you'll hear a lot more about later in the next few weeks. And then some of the kinetic theory of stellar wind shows up in other kinetic theory contexts as well. Okay, so that's kind of an overview of the different mechanisms that we'll be talking about. So I want to start by describing just a little bit empirically of what we know of the sun. This is actually a movie of the sun in white light. You can see the kind of coronal mass ejection there. This is the disk of the sun blocked out by a coronagraph. Comets do not actually generate coronal mass ejections, despite what it might look like in this movie. That's just a coincidence. The outflow from the sun, in many ways, is irrelevant for the overall dynamical evolution of the sun. The outflow now from the sun does not take away very much mass. Over 10 billion years, the sun would lose 10 to the minus 4 solar masses by its current outflow rate. And it doesn't take away much energy. The kinetic energy in the outflow of the sun is actually negligible as an energy sink compared to photons leaving the star. What turns out to be important about the solar wind is actually that the solar wind is efficiently extracting the angular momentum of the sun. The sun was rotating 10 or 30 or 50 times faster at birth than it is today, and it has lost that angular momentum by magnetic torques due to the solar wind. And that's something we'll return to. We can measure by observations like this the thermal properties of the corona, actually as a function of distance from the sun. So just to give you a feel of the numbers, at about 2 solar radii, the density is about 1 million particles per centimeter cubed. The magnetic field strength is about a Gauss. The temperature of the plasma is a few million degrees Kelvin. The energy is mostly in the magnetic field, not in the thermal energy. The energy density in the magnetic field is 100 times or more the energy density in the gas. So this plasma beta parameter is quite small. So it's actually magnetically dominated, not a thermally dominated plasma. Moreover, we can actually measure that the solar corona, at least at this distance, is not in thermal equilibrium. The proton temperature does not equal the electron temperature. The helium temperature, the oxygen temperature, the neon temperature does not equal the proton temperature. So these are just measured quantities from spectroscopic diagnostics. It's even more complicated than that. As Matt alluded to, temperatures don't need to be the same in different directions with respect to the magnetic field, and that's actually also a measured property of the solar wind. So this lack of thermal equilibrium is all a consequence of the fact that the mean free path in the corona is comparable to the size of the corona, so it's not a very collisional system. Okay. So what this tells you, if you've kind of followed along with Matt's reasoning, is that if we want to theoretically understand the origin of the solar wind, we should really worry about the magnetic field, because there's a lot of energy in the magnetic field, and we should consider kinetic theory, because it's a collisionless plasma. And what we're going to do is do none of those to start. Instead, we're going to treat the solar wind as a purely gas pressure, hydrodynamically driven outflow, a fluid driven by gas pressure. And that actually turns out to be a rather good description of the basic properties of the solar wind. And I'll describe as we go a little more why it is that despite the fact that the energy in the magnetic field is huge and it's relatively collisionless, fluid theory does an okay job, at least at describing some of the basic properties of the solar wind. So the model of the solar wind that I'm going to first start describing to you was developed by Parker in the 1950s, and it's this idea of a thermally gas pressure driven model of the solar wind. It's a very simple model. It's a spherically symmetric, steady state model for an outflow from a star driven by gas pressure. And I want to use this model to introduce some key ideas. So mass conservation. So first of all, can everybody read that? Yeah, good, okay. So mass conservation in steady state is divergence of rho v equals 0. My rho is an actual rho, not an E, unlike Matt, so notice that. Okay. So we can integrate this in spherical coordinates. This tells us, I'm going to assume there's just a radial outflow. We'll relax that assumption to take into account rotation later. For now, spherically symmetric, no rotation of the outflow. So this tells us that r squared rho times the radial velocity is equal to a constant. And in particular, that constant is the mass outflow rate, m dot, 4 pi r squared rho Vr is a constant. F equals ma now. Force balance is just that the Lagrangian acceleration, the co-moving acceleration, v dv dr, is minus 1 over rho dp dr minus gravity, gm over r squared. And I should have mentioned, actually, the notes that I sent around are 2 PDFs, one of which is these slides and the other of which is the kind of board work derivation. So that's conservation of mass, conservation of momentum. The simplest model of the solar wind, which is very wrong in detail, is to model the thermodynamics as saying just that the temperature is equal to a constant. There actually isn't a really good motivation for doing this. Maybe thermal conduction is very important because the mean free path is long. So you might think that sets up something like constant temperature. But really, this is just an algebraic simplification that gets at a lot of the key ideas. So what does this mean? Well, it means that I can write the pressure is just nkt, or that's rho kt over the average mass of particles, say the mass of the proton. I can write the pressure then as density times the speed of sound squared. So I can get rid of dp dr then in favor of d rho dr, and I can get rid of d rho dr using r squared rho v is equal to a constant. So that means I can substitute into the momentum equation to get a single equation for the velocity by getting rid of the pressure gradient and the density gradient. And that is some straightforward algebra that you can go through. It's done in the notes. And what you get is the following equation for the radial velocity. Okay, so this is 1 over v dv dr times this quantity v squared minus cs squared is equal to this stuff on the right-hand side. So this equation is at the heart of a lot of our understanding of stellar winds. It's an equation, it's called the wind equation. It also describes spherically symmetric accretion onto a point mass, Bondi accretion. Same basic physics in this equation. The key property of this equation is that if I write it in terms of the velocity gradient, dv dr, it takes the form of some numerator n divided by some denominator d. And notice that this denominator d is 0 if the radial velocity equals the speed of sound. That point at which the flow velocity equals the speed of sound is known as the sonic point. And in order for the velocity gradient dv dr to be finite at that location, I require that the numerator also equals 0. So at the sonic point, both the numerator and the denominator have to equal 0. The denominator equals 0 says the velocity is equal to the sonic point. The numerator equals 0 actually picks out a radius, and that radius, the sonic point radius, is gm divided by 2cs squared, just by setting the right-hand side there equal to, actually I think that, yeah. Just by setting the right-hand side of the momentum equation there equal to 0. Okay. So let me show you in a little more detail the kind of properties of the solutions to this equation. So what this plot shows, this shows velocity as a function of radius. One here is the sonic point. And we're interested in studying stellar winds. We're interested in solutions where the surface of the star is not moving out really fast. It's initially very slow deep in the star. So we're interested in solutions that start off relatively slow. And what you'll notice is that there's actually 3 classes of solutions of this differential equation that start at low velocity. One set of solutions, you go out, you accelerate, the velocity gradient becomes infinite, and then you come back in. So this is a solution where at the place where the velocity equals the speed of sound, the denominator is 0, but the numerator is finite, so dV/dr diverges. This is a double-valued solution also at the radius. At one radius, there's 2 possible velocities. So this is a mathematically fine solution, but a physically unphysical solution. The other class of solutions you'll notice is a set of solutions where the flow accelerates out, reaches some maximum speed, dV/dr is 0 there, and then it settles back down and the velocity goes to 0. These are solutions where at the sonic point, the numerator is 0, the right-hand side is 0, but the velocity doesn't equal the sonic point, doesn't equal the sound speed at that location. So the right-hand side is 0. The left-hand side, Vr is not Cs, so that means dV/dr is 0 at the sonic point. That's why these solutions all have 0 gradient at the sonic point. These solutions, because the flow is always subsonic, these solutions are almost equivalent to having neglected from the start this term in the momentum equation. Why? This term is of order v squared over r. This term, the pressure gradient, is of order the sound speed squared divided by r. So if the velocity is everywhere small compared to the speed of sound, then I can, to first approximation, just neglect the velocity term. And my solution for the density field is just given by hydrostatic balance. Pressure balances gravity. The problem with those solutions is that these solutions turn out to have very large pressure at large distances from the star. And so they can't match onto a realistic ambient medium. They're overpressurized relative to their surroundings. And the fact that they're overpressurized relative to their surroundings is what drives an outflow. The pressure is very large compared to the ambient pressure of gas surrounding the sun, and that continues to push stuff out, and it accelerates the flow out along this solution, which is the solution that goes through this sonic point where the velocity equals, where I satisfy both of these boundary conditions. That the velocity equals the speed of sound and the radius equals the sonic point radius. So this is the unique solution that accelerates smoothly out and matches onto a realistic ambient medium. So one of the things, so this then is kind of the solar wind solution. One of the things you'll notice about this problem in terms of the mathematical structure of this problem is that what I've done is I've varied something about the initial conditions here to get this infinite family of solutions. And what I'm really varying, this is a first-order differential equation, so what I'm really varying is the initial velocity of the outflow at some arbitrarily chosen initial radius. And what happens is the requirement that the flow smoothly accelerate out through the sonic point uniquely picks out one of this infinite family of solutions. These are boundary conditions that specify the solution. And this actually specifies the mass outflow rate from the star. If you imagine I know deep in the star what the density and temperature are from a stellar model, what I've now done is uniquely determine the velocity at that point, the initial condition for this differential equation. So if I know the density and velocity, I know the mass outflow rate. So these boundary conditions of smoothly going through a sonic transition actually specify the mass outflow rate from the star. And that's a very important property, generically, of these outflow solutions from stars. Okay, so that's really the core physics behind thermally driven outflows, like models of the solar wind. So any questions about that before I go on? I'll talk a little bit later about kind of fancy modern versions of this theory. Okay. The problem, you might think, with this theory is that why should it apply at all to the solar wind, given that I told you that actually most of the energy is stored in the magnetic field, not in the gas? So why are we neglecting the magnetic field here if there's all this energy in the magnetic field? And secondly, why am I using a fluid theory if the system is actually relatively collisionless? And so what I want to do is talk a little bit about the theory of outflows like this first, but including the effects of the magnetic field. So magnetic fields in stars, the kind of topology of the magnetic field is very complex. I'll draw you a schematic of what things kind of sort of look like. And this is actually true in the sun. There's generally both magnetic field lines that close back on the star, and there are magnetic field lines that open up with the outflow as the outflow expands out. They continue out to large radii. Now, if the sun were not rotating, okay, and I wanted to know what is the dynamics of a wind along some magnetic field line, then along the magnetic field line, what is the strength of the magnetic force acting on the fluid along the direction of the magnetic field? Zero. Okay. Trick question, right? Zero. So what does that mean? It means for a non-rotating star, you can think of this theory as really describing the flow along a given magnetic field line. If the star isn't rotating, there isn't any centrifugal force, there's no magnetic force along the direction of the magnetic field. And so this, in fact, describes the acceleration of the outflow along the magnetic field line. So what gets complicated in that scenario is really only determining this global structure of the magnetic field. What do the magnetic field lines actually look like? But this basic physics of the acceleration by gas pressure forces remains because we're focusing on the outflow along a given set of magnetic field lines where the magnetic field doesn't exert a force. Okay. So where things get more interesting is when we also now introduce rotation into the mix. So now, let's imagine the star is rotating at some rate, and I also have this complicated magnetic field structure. I'm going to now simplify this complicated magnetic field structure into a theorist's monopole, okay? So the theorist's monopole, since there aren't actually monopoles, okay, the theorist's monopole is what's called a split monopole, where the magnetic field lines go out in one direction and in the other direction. So this satisfies div B equals 0. Okay? There's no global monopole because the field lines are going out in one direction and in the other direction. And the way you can think of this, so this is kind of a toy model. Sasha Tchaikovskoy will talk about models of spinning black holes with monopole magnetic fields. It's a very simple kind of model in which the magnetic field lines have a very simple geometry. So we can actually calculate things relatively easy. We can calculate the structure of outflows along these magnetic field lines. And you can think of this as kind of an extreme limit if you initially had these dipole magnetic field lines, but there's a very powerful outflow that tries to blow open magnetic field lines. What it does at large distances is it kind of approaches this monopole-like solution. Okay. So now we have our rotating star. It has some magnetic field line. I'm going to focus on studying the properties of magnetized outflows in the equator of the star, just because that's a symmetry point. So again, it simplifies the analysis a lot. So now imagine that material, as it moves outwards, imagine that the magnetic field is infinitely strong. It's an infinitely rigid wire, so tension is infinitely strong. Then what happens, the magnetic field lines are rotating around with the star like this rigid wire. And as the outflow goes out along the magnetic field line, the material is forced to co-rotate. So as the radius increases, sorry, that's v with the subscript phi, as the radius increases, because the material is forced to co-rotate, the azimuthal velocity actually increases. And that means as well that the specific angular momentum is also increasing. So for strongly magnetized outflows, as material goes out and co-rotates due to the very strong magnetic field, the angular momentum per unit mass of the stuff that's outflowing actually goes up. And that is angular momentum that is being extracted from the rotation of the star. So what is happening is that the magnetic field is providing a mechanism for tapping into the angular momentum and rotational energy of the star and transferring it to this outflowing material. So this co-rotation continues out until the point where the magnetic field can no longer be treated as an infinitely stiff, infinitely rigid wire. And where is that point? So roughly, that's the point where the energy in the magnetic field is about equal to the kinetic energy of the outflow. And more specifically, the notes do a more detailed calculation. I'm trying to have no idea. What time did I start at? 2:15? Okay. The notes go through a more detailed calculation, which I'll sketch out a little bit of. It turns out the more detailed calculation says that the place where you stop co-rotating is where the energy in the magnetic field is about equal to the radial kinetic energy of the outflow. And the rough idea, again, is at this point, okay, at that point, there's so much energy now in the gas that you can't treat the magnetic field as this rigid co-rotating wire anymore. This point is known as the Alfvén point, and it's another kind of key point describing magnetized stellar wind. So we have the sonic point, where the speed equals the speed of sound. This is the place, the Alfvén point is the place where the speed equals the radial Alfvén speed. Roughly, which is b divided by square root of 4 pi rho. And that's the point at which co-rotation stops. Okay, so that's kind of a slightly physical or heuristic understanding of what happens in magnetized outflows. I'm going to sketch that out in a little more detail. So any questions about that physical picture?
Isn't the
Yeah, that's right. So the phi component is also important, and it turns out at this Alfvén point, the phi velocity and the radial velocity are comparable to each other. The phi velocity, or they can, actually, let me take that back. That depends on the properties of the outflows, but it actually is the radial velocity. You'll see that in the more detailed calculation. It's not the phi velocity. That comes out of the more detailed calculation. Any other questions? Okay. So the model, to kind of elaborate on this, the model is we have a rotating star. We're focusing on an outflow in the equator, again, really just for technical simplicity. And I'm going to allow the velocity to have a radial component plus a phi component. And the magnetic field also has a radial component plus a phi component. The theta components of the velocity and the magnetic field are 0 at the equator by symmetry. That's part of the nice thing about working at the equator in this model. So what we want to do now is we want to again solve our basic conservation laws to describe the property of the outflow. So just like we solved conservation of mass, momentum, and energy here, we want to now again solve conservation of mass, momentum, and energy in order to work out the properties of the outflow. So I'll just sketch out how that's done in order to introduce in a little more detail some of these ideas which were heuristically motivated here. So we again have conservation of mass, m dot is 4 pi r squared rho vr. We now have to worry about the evolution of the magnetic field. So dB dt is curl of V cross B, the induction equation. So it turns out for this setup, right, dB dt, we're doing a steady state outflow. There's no variation in time. So where did that go? So dB dt is equal to 0, so all we have to do is solve curl of V cross B equals 0. It turns out that only has a theta component, and so that's relatively straightforward to solve. So I'm going to skip the algebra. The algebra's in the notes. What that implies is actually a relationship between the phi magnetic field and the radial magnetic field, which is of this form. So B phi divided by BR is equal to V phi minus R omega divided by VR. And the way to think about this physically is that, again, consider the perfectly rigidly co-rotating limit where there's no phi magnetic field. So B phi is 0 if you're perfectly co-rotating. So the phi velocity is exactly equal to R omega. What happens, though, is if V phi is less than R omega, it means the material, which has to move along magnetic field lines by magnetic flux conservation, if the material is not quite co-rotating, V phi is less than R omega, then the magnetic field lines actually get swept back. They can't be perfectly rigid rods anymore. They get swept back, so there's a finite B phi, which is less than 0. Okay. So then the next equation that turns out to be important is the phi component of the momentum equation. And that you can show with a little bit of algebra becomes the following. So the phi component of the momentum equation tells us how does the angular momentum change. So this is the Lagrangian derivative of the angular momentum, right? It's the time rate of change of angular momentum co-moving with the fluid. As Matt emphasized, v grad v is this co-moving derivative. This is the specific angular momentum. In hydrodynamics, it would be 0. There's no torques in this pure spherical stellar wind in hydrodynamics. But with the magnetic field, there's actually a finite torque, which takes this form. So again, this just follows from writing down the momentum equation that Matt wrote down for you, and then looking at it in spherical polar coordinates at the equator. That's all I've done here. Okay, so we can integrate this equation. So if you multiply by r squared, you'll notice the left-hand side is rho r squared VR. That's m dot. That's a constant. Similarly, br times r squared for our kind of fudgy, make you nervous monopole thing is also a constant. So I can just integrate this equation. And this integral, I'll call the constant of integration L. It takes the following form. So L, which is a constant of integration for the problem, has two contributions. So this part is the angular momentum of the outflow associated with the gas. So in general, this quantity L is the specific angular momentum, the angular momentum per unit mass associated with the outflow. And there's two contributions to it. One is the angular momentum carried by the gas, RV phi, but there's also a net flow of angular momentum due to the magnetic field. Magnetic fields can transport angular momentum and energy. This is associated with the Maxwell stress that Matt wrote down. The r phi component of that Maxwell stress is a flux of angular momentum associated with the magnetic field. So in this problem, we have angular momentum carried out in the outflow both by the gas and by the magnetic field. The total rate of flow of angular momentum is a constant of integration of the problem. It's a constant of the problem. Okay. So now to figure out what that constant is, what we can do is we can substitute this expression for the magnetic field into this expression up here. And what you get is the following equation for the azimuthal velocity. Again, it's just a little bit of algebra to show this. Okay. So this is an equation for the azimuthal velocity v phi. It's normalized here to this co-rotating velocity. And you'll notice this is again of the form of one of these equations that has something in the numerator, something in the denominator, where the denominator thingy can go to 0. Okay, if the radial speed equals the radial Alfvén speed, then the denominator goes to 0. Very much like our hydrodynamic solar wind Parker model. This, though, is now the kind of mathematical expression of this Alfvén point that we talked about heuristically here. So VR the radial speed of the flow equals the radial Alfvén speed is this Alfvén point. So this kind of answers the question before of which magnetic field actually shows up in that expression, and it is just the radial magnetic field, and it is just the radial velocity. So if the denominator is 0, we need the numerator to be 0. Am I missing? No. Yeah. So we need the numerator to be 0. So the numerator is 0 means that this specific angular momentum is the radial Alfvén speed squared r squared omega divided by the radial speed squared. But at the Alfvén point, these are equal to each other. That's the definition. So that means RA here is the radius of the Alfvén point, the distance from the star where the radial speed equals the Alfvén speed. And what this tells us is that this wind solution has uniquely determined how much angular momentum is extracted from the star. The amount of angular momentum extracted from the star is given by, right, this is angular momentum per unit mass. It's given by the radial Alfvén speed squared times the rotation rate of the star. And the key thing here, and this is really in many ways the essential idea behind why magnetized outflows are so important in astrophysics, is that this radial Alfvén speed, whoops, let's see if we can not hide the interesting equation. Okay. Because the magnetic field can be very strong, this radial Alfvén speed can be much larger than the radius of the star. So what that means is the total rate at which the star is losing angular momentum, J dot, is given by the angular momentum per unit mass, L, times m dot, the rate at which it's losing mass. And that means, what is the time scale for the star to lose angular momentum? So I can define a spin down time, which is the angular momentum of the star divided by the rate at which it's losing angular momentum, J over J dot. So what is this? Well, this is roughly m r star squared omega divided by J dot, which is m dot RA squared omega. So the time scale on which the star loses angular momentum is given by the time scale on which it loses mass, m over m dot, but then it can be much smaller than that because you have this huge lever arm associated with the magnetic field torquing down the star. So this time scale can be much, much less than m over m dot because this Alfvén radius is large compared to the radius of the star. And that's the essential reason why the solar wind, which is not important currently for taking away mass from the sun, and it has not been in the previous 4.5 billion years of evolution of the sun, is in fact very important for spinning down the sun. It's this large torque associated with the Alfvén radius being large compared to the radius of the star.
Question?
Yep.
Why are you looking at the Alfvén radius in this case? What was interesting at the Alfvén radius?
So, you mean, so I guess there's several ways. You mean as opposed to what?
As opposed to the dynamics being affected. Like, why are you considering whatever angular momentum is leaving the Alfvén radius is actually lost?
So this quantity L is actually the net flow of angular momentum out in the outflow, and it's a constant, independent of radius. We got L equals a constant by integrating the phi component of the momentum equation. So there's actually a net flow of angular momentum away from the star, which is constant everywhere. So what's special about the Alfvén radius is only that because it's a critical point, I can use it to determine what that constant is. Just like we can use the sonic point to determine what the mass loss rate is in standard thermally driven winds. Okay. Yeah, thank you. Good clarification. Okay. So this idea of efficient extraction of angular momentum by large-scale magnetic fields is one that you're going to hear about quite a bit later in the week in the context of understanding jets and accretion disks around protostellar objects, compact objects, etc. Again, very similar ideas. Okay. So the last thing that I wanted to mention about these magnetized outflows has to do with energy, the energy carried by the outflow. So in hydrodynamics, so if we step back for a second, forget about the magnetic field, go back to the first problem we did, there's a conserved energy per unit mass that's a constant that is called the Bernoulli constant for those of you who've done it. And it's just equal to the kinetic energy 1/2 v squared plus the gravitational potential energy. And then it's plus this thing called the enthalpy, H, where for an ideal gas, the enthalpy is just 5/2 kT over m. kT is the energy per particle, so kT over, say, mass of the proton is the energy per unit mass. And what the enthalpy, just to remind you from thermo, the enthalpy is the internal energy, 3/2 kT, plus the PDV work that you can do, plus P over rho. So that's where 5/2 comes from. It's 3/2 plus 1. That's a detail. But that's the conserved energy per unit mass in hydrodynamics. And very roughly, for thermally driven outflows, you can think of this constant is roughly the thermal energy of the corona. So kT corona divided by the mass of the proton. Because what happens is you heat the material up enough in the corona that it's actually able to escape. Okay. Now it turns out in magnetized winds, there's an additional contribution to the flow of energy leaving the star. So what about in magnetized wind? So what's this other source of magical energy leaving the star in MHD? Yes, Poynting flux. You have magnetic fields can carry energy through Poynting flux. So that's exactly right. So there's an additional loss of energy now in the form of Poynting flux, which is again really tapping into the rotational energy of the star. So what you find then is that the conserved energy per unit mass is this hydro thing, Bernoulli, plus an additional thing, which is the Poynting flux, which I've denoted SR. It's the radial Poynting flux. That's the subscript R. And then just to get it to have the right units of energy per unit mass, it turns out the thing that matters is dividing by rho times VR. So if you go calculate the Poynting flux like you're used to calculating, what you find then is that this constant is equal to the Bernoulli constant, and then it's minus. So this is, given the magnetic field structure I've told you about, it's straightforward to calculate the Poynting flux. So it's R omega BR B phi divided by 4 pi rho VR. Okay, so I'm going to call this energy per unit mass epsilon. So just like the angular momentum flow in the outflow had both a gas contribution and a magnetic contribution, epsilon has both a gas contribution and a magnetic contribution. This is the gas contribution. This is the magnetic contribution. And in fact, this energy, the Poynting flux carried by the magnetic field, is just equal to the rotation rate of the star times the angular momentum flux carried by the magnetic field. Yep?
So we're taking the Bernoulli parameter to be conserved.
Yes.
We're also assuming that the gas is isothermal. So isn't that implicitly assuming some sort of energy source?
Yeah, so the Bernoulli parameter, so we could just as well take it to be adiabatic. So actually when I wrote down 5 halves kT over m, that was assuming it's adiabatic. There still is a conserved Bernoulli parameter for an isothermal equation of state. It's the problem, an isothermal equation of state is a little funny because there is an infinite source of energy. You're saying something is keeping the temperature constant all the way out to infinity. And so this is something I didn't want to go into, but technically what that means is that the velocity at infinity is infinity, and there's a bunch of funny things about that solution that are unphysical. Because you're right, there is an assumed infinite source of energy. That's not actually important for any of these arguments. Okay. So we have both a gas contribution to how much energy is carried away in the outflow. We have a magnetic contribution to how much energy is carried away in the outflow. So the question is, which of these is more important? And one can roughly estimate as follows. So again, just to get a feel very roughly, so the gas contribution to the Bernoulli parameter is the thermal energy in the corona. The magnetic contribution, which is this omega times the angular momentum flux. Remember, the angular momentum flux is about equal to this co-rotating Ra squared omega. So this magnetic contribution to the energy flux is roughly Ra times omega squared, which is roughly the co-rotating azimuthal velocity. So the reason for highlighting this distinction is what this means is that there's actually 2 different classes of magnetized rotating winds. There's one regime, which is the sun, which is the regime where the thermal energy in the corona is much larger than this co-rotation energy. That's the regime in which most of the energy in the outflow comes from the thermal energy of the corona. That's a thermally driven outflow. So even though the magnetic field is important for extracting angular momentum, the energy of the outflow comes from the thermal energy of the corona. And that's firmly the regime the sun is in. The decrease in rotational energy does not contribute much to the asymptotic energy of the outflow. Most of the asymptotic energy of the outflow is from thermal energy. But there's another regime you can be in, which is the opposite regime. It's the regime, whoops, this is supposed to be energy in gas is much bigger than the magnetic energy. You can be in the other regime where the energy associated with the gas is small. This coronal energy is small compared to the magnetic energy. This is the regime in which most of the energy that goes off to the outflow at infinity is actually rotational energy of the central object. So this is what I would call a true magnetocentrifugally driven or magnetically or rotationally driven outflow, where both the energy and the angular momentum of the outflow come from the rotation of the central object. And this is, for instance, jets, pulsars, rapidly rotating stars are all in this regime. So this is energy of the outflow is really rotational energy, not thermal energy. And which regime you're in just has to do really with how much rotational energy the central object has, how strong the magnetic field is, which determines the Alfvén radius, how hot the corona of the object is, etc. But this distinction really demarcates different classes of outflows that you'll see talked about from astrophysical objects. So in particular, what I'd like to stress is that accretion disks are objects where rotation is extremely important, right? It's largely rotating around in a disk. And so in those objects, outflows associated with tapping into the rotational energy turn out to be particularly effective. So that's why you're going to hear a lot later on in the week about magnetically driven outflows from rotating disks, jets, etc. Stars are thermally supported objects, and so they can be more slowly rotating, and so they can be in this regime where the outflows are actually driven primarily by thermal energy. Okay. So any questions about that? That's most of what I wanted to say about magnetically driven outflows. So there's actually more than, it's unfortunately not one. I mean, if you want to know one parameter, the one parameter is really the ratio of this thing, Alfvén radius times rotation rate. So that's a speed, a rotational speed at the Alfvén radius, to this thermal energy. But this depends on the magnetic field strength of the central object and the rotation rate of the central object. So it sort of is a one-parameter family in this dimensionless number, but this dimensionless number is in turn controlled by multiple things about the system. Yep.
I can't take my eyes off your video and the two comets.
Yes.
Are the tails of the comets tracing the magnetic field lines?
No, I don't think so.
It's ionized gas.
Yeah, it should be. So, okay, good. So the reason, so this is white, this is a white light image. You're seeing scattered light, so I assume it's ionized stuff. So what Scott is getting at is that, I mean, maybe the field lines here I would have thought would be more radial, so I'm a little surprised. Yeah, it must be, so I think the answer is you're right. It must be tracing the magnetic field lines because it's ionized gas, right?
Would it be the dust?
I mean, it could be, and I guess that could be dominating the scattered light.
I think it depends on the comet, which one it is.
Which,
That close in, I would have
Yeah. Good question. I'm not sure. Okay, so there's a homework session this afternoon. If you guys could answer Scott's question, I would appreciate it. Okay. So, any other questions about the magnetized outflows? Yeah?
This is sort of a curiosity, but some field lines reconnect on the surface, or they're closed loops.
Yes.
So there you have a geometry that at least is set up. If you can, break the flow asymmetry, then you might allow for one of the other solutions. The solution where you have two velocities for a given radius.
Yes.
Is that possible?
So what?
Those on the left.
Yeah, you might. This, I think this, I would say. I mean, this is sort of, I would say, just it's a mathematical solution that's not physically realizable. In a fluid, you can't have two velocities at the same place. You could have this solution.
Well, yeah. I was curious because there you have two radii, but if you can have a flow that.
Oh, I see. You're interpreting, yeah. So I think it is true on closed field lines you get very different dynamics. I think it's actually closer to hydrostatic equilibrium, so it would be more analogous, if anything, to one of these. Okay. So I wanted to briefly mention why we use fluid models at all. So I kind of addressed the question of why should we believe a fluid non-rotating model of the solar wind, given that it's magnetically dominated. The answer to that is that the sun is very slowly rotating. The acceleration along the field lines is just gas pressure. Magnetic fields don't contribute to acceleration along the field lines. So that's why, even though it's magnetically dominated, it's okay to first approximation to not worry so much maybe about the magnetic fields. What about this question of why are we considering a fluid theory at all, given that it's actually a collisionless plasma? And the honest answer is that this is a really active area of work, and we don't exactly know when it's a good approximation to use a fluid theory and when it's not a good approximation to use a fluid theory. So I'll give you a few heuristic arguments which suggest that maybe using the fluid theory is okay, even though it's collisionless. Yep. What defines slowly rotating enough is really this comparison. Thermal energy relative to rotational energy at the Alfvén point. Okay, that's really the key thing. Yep?
At one point, you were using V times R squared to be constant.
Yes.
If there's a dipole, V should go down at R cubed.
Yes, that's right. So I erased, thankfully, my monopole, which shouldn't be up there. So this is the split monopole approximation, and it's one of the real limitations of this model. It's the approximation that the magnetic field lines are actually opened up in the outflow and are closer to a monopole rather than a dipole. That's right.
But we can measure the magnetic fields at different points.
That's right. And that's right. So close to the sun, it actually opens up faster than even 1 over r cubed. And that's because the magnetic field lines expand out like this. And then further from the sun, it's close to a monopole. So it is kind of, the radial magnetic field is dropping roughly like 1 over r squared. Okay. So the collisionless question, so I'll give you 3 not totally satisfying arguments as to why fluid theory is maybe okay. So the first is that in 2 directions, perpendicular to the magnetic field, the Larmor radius is really small, so particles can't actually travel large distances. They spiral around the magnetic field, like Matt showed. So in some sense, the strong magnetic field, in the sense of a small Larmor radius, limits how far particles travel. And so it's really only in 1 direction out of 3 along the magnetic field line that you have this long mean free path where you might think fluid theory would catastrophically break down. So, okay, 2 dimensions out of 3, maybe we're okay, 1 we're not. The other is that along the magnetic field in the case of the sun, the dominant acceleration is due to pressure, and whether we model that pressure as a scalar or as a tensor, right, if we roughly know the magnitude of that pressure gradient, we'll roughly get the acceleration right. And so fluid theories do okay at a factor of few. They're not going to do better than that because the pressure is really a tensor and not a scalar, but the fluid theories might do okay at the factor of few level because they're getting right that they're getting the basic acceleration mechanism of the solar wind correct, which is the pressure gradient. And then the last one, yep.
I'm sorry if I'm confusing something here, but what mediates this pressure force? Isn't it collision?
So yes and no, right? So a system of stars in a galaxy you can model as being in hydrostatic equilibrium, pressure balances gravity, even though there's no real collisions between stars. So even in a collisionless system, you do have a pressure force. It's mediated really by the electromagnetic field. That's really what's doing the mediation. But you still have, you still have thermal energy, you still have gradients in thermal energy, which produce a net force on the material. The other way to say that is when you take moments of the Vlasov equation like Matt did, even in kinetic theory, you end up with a pressure tensor which balances gravity. Or in the case of a wind, doesn't balance gravity. That's why you get a wind. The last point is in some ways the one that's an area of a lot of current research, and it has to do with, again, something that Matt alluded to, which is that if the distribution function tries to get way out of thermal equilibrium, very non-Maxwellian, temperature is very different in different directions, a very skewed distribution function, it turns out there's all kinds of instabilities in the plasma which set in and try to wipe out some of those large deviations from Maxwellian in the distribution function. And so again, this helps make the system behave a little bit more like a fluid than you might otherwise think. So in detail, to model the solar wind correctly, we clearly do need kinetic theory, but to get some of the key ideas and to get an order of magnitude understanding of what's going on, fluid theory actually works reasonably well. And I think, although don't know, that it's some combination of these kind of three basic reasons. But this is, as I alluded to, this is actually an area still of active research. Okay. I wanted to end the discussion of winds like the sun just by mentioning kind of the state of the art in thinking about models of the solar wind. And really the state of the art is in understanding how in detail the solar wind is actually heated, producing the hot corona, which produces an outflow because there's large pressure in the corona. So that step of heating goes to pressure, goes to acceleration of the solar wind. This step is in many ways the kind of critical step that people are trying to understand. And one of the interesting empirical facts is that this heating is actually measured to extend not just in the corona, but it extends all the way past the Earth in the solar wind. So this is a measured temperature profile. The kind of ratty thing is the measured temperature profile from the Voyager satellite as a function of distance from the sun. So this is the Earth, and this is much further out in the solar system. This is the adiabatic temperature profile. And you see that the temperature profile is shallower than adiabatic, so there's heating going on. So there's actually heating extending over a wide range of radii. And the best guess, although, again, this really is an active area of research, the best guess is that there are waves launched by the sun which travel out into the solar wind and they damp over a wide range of radii, producing this very spatially extended heating. And kind of the favored models are ones in which it's mostly Alfvén waves, which are carrying the energy from the sun out to large distances. And so the physical picture roughly is that this dynamic activity in the solar convection zone and the surface layers of the sun, so this is an actual movie of convection in the surface of the sun, that shakes around the magnetic field lines, which launches waves out into the corona, carrying energy, again, basically by Poynting flux, carrying energy out into the corona, which ultimately, some of those waves damp, heating the material and producing an outflow. And so trying to understand this excitation of waves, how the waves damp, and thus produce the acceleration of the solar wind, that's where a lot of the activity is in kind of detailed models of the solar wind. Okay. So that's all I wanted to say about winds driven by thermal energy and magnetic energy. I wanted to just talk briefly about winds driven by radiation pressure. But before I go, just make sure, any questions about thermally magnetically driven winds? Yep.
How much of what you've done here runs backwards?
How?
If you do the accretion matches you get, sorry, if you do the ring matches the accretion.
Yes, that's right. So
Thing run backwards.
that's right. I didn't stress that, but this kind of mathematical solution for Parker's thermally driven solar wind, the time reverse of that is spherical Bondi accretion onto a central point mass, which is a kind of important model that has shaped some of our understanding of accretion, at least without angular momentum. There are also solutions for inflows associated with large-scale magnetic fields, which are very much analogous to the Weber-Davis model, but describing an inflow onto a central object. The principal difference is we think that accretion disks are largely rotationally supported at large radii, and this model is not actually a rotationally supported model. So it's not as good an analogy to time reverse this as it is to time reverse the thermally driven case. Yeah, that's a good question. Okay, any other questions? Okay, so the other way that you can get outflows, so what we've talked about here is ways of tapping into energy, the thermal energy of a corona, the rotational energy of a star. The other way that stars drive outflows is actually by tapping into the momentum of the stellar photons. And there's really two ways that this happens. The first is in giant stars, stars that are on the red giant branch and the asymptotic giant branch. If you don't know what that means, don't worry about it. These are just stars like the sun. Later in their evolution, the sun will expand to become a giant. It'll incinerate the Earth probably, things like that. When it does that, the surface temperature of the star decreases significantly to a few thousand degrees Kelvin. And above the photosphere, so out in the atmosphere of the star, the temperature drops enough, it drops below about 1,000 Kelvin, where you can actually start to form large solids, so dust grains. And the reason that that's important is that it turns out that these large micron-sized particles are very effective at absorbing optical and ultraviolet photons. So they have a cross-section for absorbing the stellar light that is much larger than the ionized gas that was otherwise in the stellar photosphere. So you create all this dusty stuff in the stellar atmosphere. Suddenly, that material very efficiently absorbs the photons coming from the star. You absorb all of the momentum generated by the star, and the luminosity of the star can greatly exceed the Eddington luminosity associated with this dust. And so you can drive a very powerful outflow by having the photons get absorbed by the dust, and the dust is then collisionally coupled to the gas. So this is actually the dominant way we think that a star like the sun loses mass at the end of its life. The sun will become not a 1 solar mass white dwarf, but maybe a 0.6 or 0.7 solar mass white dwarf, and most of that mass is lost in outflows like this. The other way we know of tapping into the momentum of stellar radiation to drive an outflow is that in massive stars, in the atmospheres of massive stars, you have, given the temperatures of 30,000 degrees Kelvin, 20,000 degrees Kelvin, you have many absorption lines due to heavy elements like iron and nickel and oxygen. And those absorption lines are so efficient at, again, absorbing the stellar light that the luminosity is larger than the Eddington luminosity, and so you can drive an outflow. Okay? The radiation pressure exceeds gravity. Again, if you haven't seen it, luminosity exceeding Eddington luminosity is equivalent to saying that the net transfer of momentum from the radiation field to the gas exceeds the gravitational binding of the gas, so you're able to drive an outflow. So these are both the same idea. You deposit more momentum in the gas than the gravitational binding energy. It's just mediated by different ways of absorbing the radiation, kind of micron-sized solids and metal lines. And this bit of physics here is critical for determining which stars, when they collapse, have enough mass that they'll collapse to form a black hole, which stars have lost so much mass that they'll collapse to form neutron stars instead. Okay. So I want to give you just a few heuristics for how to think about what sets the properties of these radiation pressure-driven outflows. So in thermally driven outflows, we talked about how the energy in the outflow, which is given by, at large radii, that's given by the mass loss rate times the kinetic energy of the outflow. But really, that energy is whatever the thermal energy of the corona is. That's this argument here that for thermally driven outflows, the energy is equal to the thermal energy of the corona. So that's saying the energy loss rate is about m dot times the speed of sound squared, which is just kT over m. For radiation pressure-driven outflows, the heuristic, the way to think about it is different. It's really that the order of magnitude estimate is that the momentum flux in the outflow, so what is the rate at which the outflow is carrying away momentum, that's the mass loss rate times the velocity, that's given roughly by the momentum in the stellar photons. So each photon has a momentum which is h nu over c, energy divided by c. So the rate at which the star is kind of losing momentum to photons is L over c. And so roughly the momentum flux in these radiation pressure-driven outflows is roughly L over c. And the prefactor in front here depends on how efficient these various coupling mechanisms are. And then, because the radiation force is overcoming gravity by a factor of order unity or a factor of a few, the speed you end up with at infinity is about the escape speed from the object. And so this is an extremely useful heuristic for thinking about what sets the properties of these radiation pressure-driven outflows. Speed is about escape speed. Momentum flux is about photon momentum. And if you plug in numbers for stars that are big, puffy giants, you get mass outflow rates of maybe 10 to the minus 4 solar masses a year, 3 times 10 to the minus 5 solar masses a year, which is similar to what we see, speeds of tens of kilometers a second. The speeds are low because these are really big stars with radii of 1,000 solar radii or so. So the escape speed is very low when they're a giant. By contrast, massive stars on the main sequence have similar mass loss rates, 10 to the minus 5 solar masses a year, but they're much more compact. They have larger gravity, so they have much larger velocities of order 1,000 kilometers a second. Okay. Question?
Is there a physical property to infinite speed?
Sorry. V infinity is the speed the material has at very large radii. It's kind of the asymptotic, quote, speed at infinity. It just really means the speed at large distances where it's stopped accelerating anymore. Any other questions? Okay. So I want to quickly actually derive this because it's kind of a cute few-line derivation. So here's the idea. So we're going to write down the momentum equation, which has a gas pressure force minus gravity. But now there's also a force due to the radiation field. And the force due to the radiation field depends on the rate at which momentum, so the flux divided by c is again related to this, what is the rate at which momentum is flowing out in the photons. And then kappa is the opacity. This has units of centimeters squared per gram. It tells you how efficiently does the material absorb the photons. And really, what this should be is something that's averaged over wavelength, and Jim will probably maybe talk about that when he talks about radiation hydrodynamics in more detail next week. That really this quantity on the right-hand side here is some average over all the wavelengths in the radiation field from the star. Okay, so now I'm going to do something kind of drastic just to give you a very simple derivation. Is I'm going to ignore gas pressure and I'm going to ignore gravity. I'm going to say all I have is this outflow driven by radiation pressure. Okay? Just for simplicity, just to give you a feel of where this result comes from. So VdVdR then is kappa L over 4 pi r squared c. The flux, I'm assuming we're in the regime where the flux is just L over 4 pi r squared. I don't have to do any fancy radiative transfer to calculate the flux. So what I'm going to do now is I'm going to just multiply both sides by 4 pi r squared rho. So on the right-hand side, I get 4 pi r squared rho v times dVdr. That's equal to rho kappa L over c. 4 pi r squared rho v. That's just my mass loss rate. Now I'm going to integrate this over all possible radii. And I get m dot times the velocity at large radii v infinity. So I integrate this over all radii. I get the velocity at large radii minus the velocity at small radii. Drop the velocity at small radii. This is equal to something that I'll write as tau times L over c, where tau is this integral of rho kappa dr. So if you've seen this before, this is called the optical depth. It's a dimensionless measure of how much absorption or scattering due to the radiation there is. So roughly speaking, the mean free path of a photon, well, the mean free path of a photon is 1 over rho kappa. So this tau is something like, just approximating the integral, it's something like the size of the system divided by the mean free path. It tells you how many absorptions or scatterings there are. So what this shows is that the momentum flux in the radiation field, the momentum flux in the outflow, m dot v infinity, is L over c times this coupling coefficient, tau, which tells you how many scatterings there are. And so that's the kind of uncertain dimensionless coefficient I was talking about. So that's really where this result comes from. Okay. Very briefly, let me mention, for massive stars, there's a very kind of interesting bit of physics that goes into generating these winds, and it's as follows. If you have a static atmosphere, and you have a bunch of absorption lines due to atomic transitions, what determines the net opacity is how many lines there are and how broad they are. Because how broad they are determines whether a photon of a typical frequency will actually get absorbed or not. The breadth of the line in a static atmosphere is determined by thermal broadening, just the temperature. When you start to get an outflow, though, you get this interesting situation where the acceleration of the outflow produces a velocity which generates large Doppler shifts between different parts of the wind, and you get into a regime where the Doppler shifts that determine the probability of photons getting absorbed are not thermal broadening anymore, but it's actually Doppler shifts associated with the outflow. And in particular, if the lines are broader because of the Doppler shifts, you're able to absorb photons more effectively, which means you get more acceleration, which means the velocity goes up, which means you get more Doppler shifts. And so this bit of physics is kind of at the heart of understanding these winds driven by radiation pressure on lines from massive stars. And the notes describe this kind of physical description. They go through the notes go through it in a little bit more detail. This also changes some of the mathematics of the critical point structure that we talked about. That's something that I didn't go through in the notes, but if you're interested, send me an email and I can send you some references on that. Okay, so I have 1 minute or negative 2 minutes left. The last thing I wanted to do, because I think this actually is important, is I wanted to stress a few ways in which the ideas in the context of stars that I've emphasized in this lecture actually apply to totally different problems in astrophysics, and how you can carry over the physics that we've talked about here to a wide range of other interesting astrophysical problems. So I'll just mention a few. So this is actually an example from work that Drummond Fielding, who's here, is doing. This is understanding outflows from galaxies. So rather than being a star, which has the radius of a sun, this is now a galactic disk that's a kiloparsec in size. And what Drummond has done is blown up a bunch of supernovae. This movie shows density, this movie shows temperature. And what this is doing is just putting a bunch of thermal energy into the galaxy, creating a big hot galactic corona, which then expands out, generating a thermally driven galactic wind, exactly like Parker taught us. So the physics here is extremely similar to the Parker model of the solar wind. This goes back to work by Chevalier and Clegg in the mid-'80s, where they basically just applied the Parker wind theory that we developed here to understanding galactic winds. And this is still, in many ways, one of the leading models for our understanding of outflows from galaxies driven by star formation, which have a huge effect on our understanding of galaxy formation. The temperature of the outflow gets up to 10 to the 8 Kelvin in the hottest regions.
This is realistic.
Yep. Yes, I agree. Okay. The other is we see from accreting supermassive black holes, quasars, we see very fast outflows, velocities of tens of thousands of kilometers a second. These outflows are measured to carry away a significant amount of momentum. The measured momentum flux in the outflow, m dot v, is of order L over c. As we've talked about, speeds are 10,000 kilometers a second. We think these powerful outflows from accreting black holes can, again, have a large effect on the interstellar medium of their host galaxy and affect how galaxy formation operates. Our best model for how these outflows are generated is taking this model of line-driven winds driven by radiation pressure on lines, and simply applying it, instead of to a spherical geometry of a star, applying it to the geometry of a disk. Okay? It's a very nice paper. I can kind of make fun of it because Norm Murray's a good collaborator and friend of mine. But really, they did just take the stellar wind theory and apply it to a disk, right? It was a great idea, and it's our best understanding of where these powerful outflows from accreting supermassive black holes, the ones that carry a lot of mass at least, where they come from. Perhaps what will be most important for the remainder of the next few weeks is that our understanding of magnetized outflows from accretion disks, neutron stars, even how to tap into the rotational energy of a black hole, those models are based on the Weber-Davis model of magnetized stellar winds that I just described to you. In fact, if you go back and you read the seminal paper at Blanford and Payne, which describes magnetized winds from accretion disks, the introduction explicitly says that what they're doing is applying the Weber-Davis model to disks. And so this general idea of extracting rotational energy by large-scale magnetic fields is a really critical component to our understanding of accretion disks and jets. And in fact, I would argue that one of, if not the biggest uncertainties in our models of accretion disks is understanding the relative importance of large-scale magnetic fields like these, shown in Sasha's simulation, or Roger's cartoon, okay? Whether the angular momentum transport is dominated by these large-scale magnetic fields or smaller turbulent magnetic fields in the accretion disk produced by things like the magnetorotational instability. And this is something that you'll hear a lot more about. But our kind of understanding of this physics of tapping into the rotational energy of the disk, the core idea is the idea I just told you about, how magnetic fields tap into the rotational energy of stars. Okay, so that's it for this lecture. Next time we'll actually talk about a rather different topic, instabilities in fluids and plasmas. So thanks very much. Any other questions?